Welcome to Sri Learning Academy. Let's simplify race condition. Imagine two people trying to edit the same bank balance at the exact same time. One adds money, the other withdraws money, and both believe they are correct. But when the final value appears, it is wrong. No hardware failure happened, no program crashed, and no one intentionally made a mistake. The real problem is timing. And in operating systems, timing bugs are some of the most dangerous bugs because they can hide for a long time and appear only under certain conditions. This is where we meet one of the most important concepts in synchronization, the race condition. A race condition happens when two or more processes or threads access shared data at the same time, and the final result depends on the order in which they execute. In other words, multiple execution paths are racing to use the same resource. If the order changes, the result may also change. Sometimes the output is correct, sometimes it is wrong, and sometimes it fails in unexpected ways. That uncertainty is what makes race conditions so serious. They are not always visible during testing, but under real workload, they can create random errors. To understand this clearly, think about a shared counter variable called count, whose current value is 5. Two threads want to increase it by 1. At first glance, you may think the final answer should become 7, but increasing a variable is not one single magical action. Internally, it usually happens in steps: read the value, add 1, then write the new value back. If thread A reads 5 and thread B also reads 5 before either writes back, both will calculate 6. Then both write 6. Final answer becomes 6 instead of 7. One update was lost. This is a classic race condition. This happens because shared data is being modified without coordination. The variable is shared, but access to it is uncontrolled. Earlier, when we discussed processes and threads, we learned that modern systems run many tasks concurrently. The CPU switches rapidly between them, and on multi-core systems, many tasks truly run in parallel. That improves performance, but it also creates situations where multiple execution units touch the same memory at nearly the same moment. If the OS or programmer does not synchronize access, inconsistent results appear. Let us take a banking example because it feels real. Suppose your account balance is 10,000. One transaction deposits 2,000 while another withdraws 3,000. Correct final balance should be 9,000. But if both transactions read the old balance of 10,000 independently, the deposit may write 12,000 and then the withdrawal may write 7,000, or the reverse may happen. Depending on timing, the final balance may become 12,000 or 7,000 instead of 9,000. Imagine this happening in a real bank system. Even a tiny timing issue can become a major financial problem. Race conditions are not limited to banking systems. They appear in printer queues, ticket booking systems, inventory management, multiplayer games, and operating system kernels themselves. Suppose two users try to book the last movie seat at the same time. If both requests check availability before the seat is marked as sold, both may receive confirmation. Now, one seat has two owners. The root issue is still the same: shared data accessed concurrently without proper control. Inside an operating system, race conditions can be even more dangerous because the shared data may be process tables, memory maps, file system metadata, or scheduling queues. Imagine two kernel routines updating the ready queue at once. If one insertion overrides another, a process might disappear from scheduling temporarily. Or imagine two tasks updating a file allocation table incorrectly. That can damage files. This is why synchronization is a core topic in OS design, not just application programming. Now, an important question arises. If the CPU executes instructions so fast, why can't it just finish one task before another begins? The answer is multitasking and interrupts. Operating systems constantly switch between tasks to improve responsiveness. A thread may start updating data, then get interrupted. Another thread runs and accesses the same data. On multi-core processors, two threads may literally execute at the same time on different cores. So the issue is not speed alone. The issue is overlapping access to shared resources. This naturally leads us to the idea of a critical section, which we will study next in depth. A critical section is the part of a program where shared data is accessed or modified. If race conditions happen, they usually happen there. In our counterexample, the read modify write steps form the critical section. If only one thread is allowed inside that section at a time, the problem disappears. So race conditions explain why critical section solutions are necessary. Detecting race conditions can be frustrating because they are often inconsistent. You may run a program 10 times and see no issue, then the 11th run fails. That is because the timing between threads changes depending on CPU load, memory state, interrupts, and scheduling decisions. These bugs are sometimes called Heisenberg bugs because observing or debugging them can change their behavior. Add a print statement, and suddenly the bug disappears because timing changed. So, how do systems prevent race conditions? They use synchronization tools that control access to shared resources. These include locks, mutexes, semaphores, monitors, condition variables, and atomic operations. The main goal is simple. When one thread is modifying shared data, others must wait or coordinate safely. Later topics like Peterson's algorithm, semaphores, and mutexes are all solutions built to solve the problem introduced by race conditions. However, fixing race conditions must be done carefully. If we lock everything too aggressively, performance suffers because threads spend time waiting. If we design locks badly, we may create deadlocks or starvation, which are problems we will study later. So, synchronization is always a balance between correctness and efficiency. First, we need safe behavior, then, we optimize speed. In simple terms, a race condition is a shared data problem caused by uncontrolled concurrent access. Multiple tasks race to read or update the same resource, and the final result depends on timing rather than logic. That makes the system unreliable. Once you understand race conditions, you understand why operating systems need synchronization mechanisms so badly. Without them, multitasking systems would be fast but chaotic. And with that foundation, we are ready to move into the next concept, the critical section problem, where we learn how operating systems bring order to concurrency. That is it for this video. See you in the next one.